Ever wondered how a model in machine learning learns to make accurate predictions? Well, buckle up as we dive into the world of underfitting, overfitting, and the bias-variance trade-off. Imagine a graph with data points scattered across the x and y axis. These points represent the different outcomes of a specific event. We have our x-axis representing an independent variable and the y-axis representing a dependent variable. The goal here is to make a model that can predict the y value given an x value, output. Now picture a straight line running through the middle of these points. This line is our machine learning model. But oh no, it seems like our model is missing a lot of points. It's not capturing the complexity of our data. This is a classic case of underfitting. The model is too simple to capture the underlying relationship in the data. So we try again. This time we plot a line that passes through every single data point. Perfect, right? Not quite. This line is a bit too enthusiastic. It's not just learning the underlying pattern, but also the noise in the data. We call this overfitting. While it might seem great on our training data, it will perform poorly on new, unseen data because it's too tailored to the specifics of our training set. Now, we're at the crossroads. We don't want our model to be too simple nor too complex. So what's the solution? It's a balancing act, my friends, one that has been aptly named the bias-variance trade-off. Imagine a line that doesn't pass through every point, but rather, it captures the general trend in our data. It's a line that's flexible enough to learn the underlying patterns, yet restrained enough not to get swayed by the noise. This line represents the sweet spot of model complexity, where the error from bias and variance is at its minimum. This is the bias-variance trade-off, the balance we strive to achieve when training our models. So, to sum it all up, underfitting is when our model is too simple, missing the underlying trends in the data. Overfitting is when our model is too complex, capturing the noise along with the patterns. The bias-variance trade-off is the sweet spot between these two extremes, where our model is just complex enough to accurately capture the underlying patterns without getting swayed by the noise.